So good afternoon, everyone. Yes, I'm excited to be here. I was actually here almost a year ago in November for a sort of informal seminar while I was still deciding on this opportunity. And then I arrived here in July, and so it's been just been really fun. So we're starting a series of conversations to understand where I fit the best in Eawag. And the truth is that I think I fit in a lot of places, and maybe none of them very well because I do a lot of different things, but they're all around river systems. So one of the things that I'm most interested in is rivers, particularly rivers within watersheds, within coastal areas, from kind of the science and the processes that regulate rivers, that form rivers and evolve rivers, all the way to the way in which rivers impact people. So I selected a few topics. So I have to say I had a very warm welcome in Europe, which has been even warmer than I expected. And I have a lot of invitations for talks. So between last week and January, early February, I'm giving 9 talks. So there's a lot of different pieces. So I'm going to go also to WSL. I'm going to go also to the Department of Environmental Science at ETH. So I get bored giving the same talks. So it's not maybe the most efficient way because I'm going to spend a lot of time preparing talks. But all these talks are going to be quite different and trying to target the things where I think there's the most connections with the audience. So this is to say that this is a snapshot of things I work on where I think there's the most connections, but I could also have made completely the wrong choice. So if you see other things that are listed that you really want to hear about, hopefully we'll leave enough time for discussions and we can dive into any other topic. The landscape that you see there, I'm actually not going to use it as much, but it is one of the few examples where I did have remote sensing modeling and observations and graphs from the same place. This is a river delta, so I do a lot of my work in coastal systems, and this is actually a place in coastal Louisiana that you'll see pop up again in the talk. And so the main problem I'm interested in, and with that, with my group, is kind of like this coexistence of people and river systems. And the fact that historically, and we know that people have always moved next to water, and that comes, of course, at the expense of making modifications. Of course, people benefit a lot from being close to water, but also eventually live a little bit too close to water, and we'll talk about that. The pictures are some examples. Mostly I took them, or I purposely chose also the place where I'm originally from, which is Genova, which is the bottom picture. The top is Bangladesh. That's a country where I did a lot of my work for the last decade. And that's an example of an embankment, so a flood protection, and with people right there. These embankments, I won't talk about that today as much, but of course they lead to a disconnection between the river and the floodplain, and does land loss within these islands, and that creates even more issues with flooding. The second picture I took on the seal while running. So of course you can see a roof there. So there's a lot of urbanization. I would say European cities always, we have a lot of urbanizations around rivers. Genova, the city where I'm originally from, so I am Italian, although I spent my last 22 years of life in the United States. But Genova is a place where we built actually on top of the river. So the river actually is buried for most of its course, and you can argue that tunnel is probably undersized for the events that we're going to see. So lots of issues, lots of very fast flood events. And this is a picture from more of a perspective paper that we wrote a few years ago with a former postdoc of mine. And it's about really when we make these modifications to the system, and then when we go and restore river systems, we kind of try to replace processes that are naturally acting, like, for example, rivers like to evolve, they like to change course, and this happens under specific set of conditions. That is beneficial. Sometimes that's how, for example, if you're familiar with, lots of the coast, or like, for example, coastal Louisiana was built that way through the Mississippi, essentially evolves in different locations over many years. When we go and restore systems, it's pretty hard to replace these larger scale processes. So I kind of like, most of the things that I have in mind are really what happens when you have communities and rivers next to each other. This is getting worse, of course, through time, because a lot of these systems are under stress. And with that, I mean watersheds, I mean rivers, but also ecosystems that live there. Sediment dynamics are changing. This is an example of a paper that I use very often. It was an analysis done on the magnitude of the 100-year flood and how it's expected to change under essentially 21 different climate projections. So you see in red is a case in which the magnitude of that associated with the return period would decrease. In blue is the magnitude would increase, and the intensity of the color is how much agreement there was among the 21 models that were used for that. The point is that you see a lot of changes that are happening in many watersheds, and so these are impacting the ecosystems, the people living there, and also all the sediment transport, and thus the possibility of building land and what's happening in those areas. And in particular, these hazards, so I like to think about hazards a lot, and so these hazards can be chronic or can be acute. So communities are exposed to things that are always there, and so you can think about sea level rise, you can think about pollution, you can think about erosion, migrations of rivers, and things like that. But it can also be acute stressors, and that happens when you have a flood event or a particular release of a pollutant, for example. And so through time, you will see this in one of the chapters of this talk that I will present. I started predominantly as a flood person, working on flooding. And then as I started working with communities, realized quickly that I could not just isolate flooding, because flooding was not the only issue people were dealing with. And so we started doing a lot of work in thinking about hazards and multiple hazards happening at the same time. So one thing that I often think about then is this contrast between what is stable, so what stability means, and that's often what communities aim to achieve. So often when we live next to a river, we want the river to stay exactly where it is, the way it is. That comes with a price, because normally the way river systems work and shape landscapes is really through migrations and movement that really feeds the floodplain with water, with nutrients, with sediments. And so normally these modifications of the network dynamics often actually enhance flood events more than before. So there are many cases like Bangladesh, for example, the flood protections enhance the tidal signal. There's cases in the Mississippi where it has been shown that human modifications have led to larger floods than we would expect just based on climate. What landscapes would like to have is being sustainable. So there's a big difference between something that is stable and something that is sustainable. When we take the landscape view, sustainability means that rivers are able to shift, they are able to disperse water and sediment in the floodplain. That comes at an expense of the fact that rivers move around, people live there, and that does become an issue, right? It wouldn't be as much of an issue if the river was to move around and then nobody was living there, because then it could expand as much as it wants. But in this case, with communities, that becomes a conflict. The spatial and temporal scales associated with this conflict, and of course, the restoration interventions that are equally complicated. So the work that we do as a group is kind of around this main theme. I'll go specific in 3 specific projects. But as a whole, I would say myself and my group are interested in understanding rivers and river systems, river networks, from the perspective of Earth surface processes. So there's a part of me that is a little bit more geomorphological, which I won't show as much today, but also all the way to how then we provide information at the network scale to really inform then adaptation strategies or help communities develop strategies for what's going to happen in the future. So the selection that I made is kind of aligned with these satellite graphs and models, although honestly, there's satellites, there's graphs, and then models in each of these chapters, so they're absolutely not separated. I also use field observations, so all the things are very much mixed. But I'll talk a little bit about multi-hazards and detection of floods and heat events, and how potentially to detect these events and potential equity issues associated with them from satellite observations. I'll talk a little bit about SWOT and the SWOT mission in the second chapter, and I'll talk about what that mission is and what it does, and particularly in the context of what I thought would be closer to Eawag. So instead of talking about necessarily only water and sediment, I'm going to go into nutrients, provided that my chemistry is really bad. So I'm looking forward to hearing how we can improve these type of approaches. And then the third part is going to be on models, particularly on humans and human interactions with landscape. So each of these parts, I think, is roughly going to be 10 minutes. So you can decide which one is your favorite and pay attention only to that one, or you can just listen to all of them together. But hopefully this will give you breaks. All right, so multi-hazards event. So as I said, the context for this, so differently from the talk that I gave here last year, which was a little bit focused on, when I talked about this project, I talked about how it's organized because I was talking about how I manage a large-scale project. This time I'm actually going to focus mainly on the science. But the context of this specific chapter, and actually another one as well, is this Southeast Texas Urban Integrated Field Lab. So disclaimer, I got here in July, so a lot of my projects are still funded by the United States. So all the science that you will see today is science that is very much ongoing, with the people that are doing it being actually here in the room. So I chose that on purpose, but of course the funding agency are American. And so the Urban Integrated Field Lab, this was a large-scale call from the Department of Energy. And it was about focusing on hazards under changing climate, and the impacts on marginalized communities or groups that are less advantaged. And this call came out 2 years ago or so. 4 years ago, actually. And so we were one of the centers funded. There's 4 centers in the United States. I'm the lead of the Southeast Texas one. I remain the lead from here. The center is about 90 people, to give you a scale, and embeds all sorts of disciplines from like the more engineering side all the way to the social science side. The things we're interested in, so we're working in Southeast Texas, particularly Beaumont and Port Arthur. You see a snapshot here. An area that carries a lot of weight in terms of energy production in the United States, so very important from an energy production point of view, but also very much of a hotspot for pollution, many issues in air quality, and lots of issues of flooding because you're right at the coast. So this is an area that experiences compound flooding, so rainfall, rivers, and coastal flooding. And also big air quality issues. In fact, people that live here, when they do their annual physicals with doctors, they actually get a lung scan every year for lung cancer, which is not necessarily a very common thing in other parts of the world, or at least in the United States. And so the big science questions that we're focusing on, it's a very nested approach, a very nested project. So we're going from the human scale to the whole regional scale, because we're looking at atmospheric processes and hydrological processes, so we need to get right. So we have these larger scale models, but we also need to inform the resilience at the human scale. So we are focusing on the variables, the processes that really matter across scales. And also we need approaches that kind of combine the human, the social, and the kind of like the urban side, the natural side, and the social side. So within this broad scale project, so historically, when I started doing flood work, and so this goes back all the way to my PhD. I spent my PhD thinking about how to extract networks from high-resolution topography data. So these were like the 2000 something. I finished my PhD in 2009. At that time, high-resolution topography, meaning terrain data with at least 1 meter resolution or below, had just exploded, and essentially people didn't know what to do with them because there were this massive amount of data. And so I spent my PhD doing this type of approach that you see in the equations on the left. So in thinking about how to re-extract channel networks with approaches that come more from image processing. So in thinking about them as geodesics, so a line of minimum cost where the cost is specific of the feature you want to extract. And so in that way, we were able to extract channels based on curvature, based on flow accumulation, and essentially these would help us with a lot of the barriers and things that you see in LiDAR data. You see dams, you see bridges, you see the other things. That evolved into doing flooding. So essentially what we would do is to take these improved center lines, and I do a very simple approach for flooding. Why was that needed to be simple is because one thing that personally keeps me up at night, and it has had for a long time, is the fact that we have done research on flooding for many decades. We published numerous papers, many, and still people die from flooding. And not only is in developing countries that maybe don't have data. There was the July 4th flood in the United States that you probably have seen. This was in Texas, in fact. There were a bunch of girls, hundreds of girls, just spending the summer on the floodplain of the river, and many of them died. And so that kind of gave me an inspiration to do flood work simpler. So flood work that was probably harder to publish on water resources research, but flood work that could be co-developed with firefighters. So a lot of this work actually brought firefighters in, and we actually co-developed maps and tools that they could be using on the ground. And in fact, they are. So what I mean is that we take these improved center lines, and now we essentially calculate, how high is the terrain with respect to the bottom of the channel, and so at what height the location is going to be flooded, and essentially estimate flooding that way. It's very simple, it's very computationally efficient, and that's how we do fluvial inundation, so from rivers. Then there we attached a pluvial component. This is not a tool that we developed ourselves, but it came from a different group. And essentially what they do is, again, they use high-resolution terrain data to detect depressions in the terrain, and then develop a hierarchy of these depressions so they can route flows through the depressions and essentially get a sense of what accumulation of water you see from rainfall. And now we developed a third approach from the coast, same kind of bathtub approach. So you're essentially flooding based on terrain and some connectivity constraint, and we develop a coastal approach. And all of these are combined into these tools that were just pieces of this have existed, as I said, for many years, but we're essentially just putting out a new version that is just a set of library that is very easy to install. And it's called PyGeoFlood. And this image actually here just shows an example of a comparison with the ETH-Zürich, which is a known model for coastal flooding. And essentially what you see is we overestimate a little bit. There's some of the green that is false positive, but to be a tool that runs so fast, it actually does a pretty decent job at a first cut of what the flooding might look like. This is not something that you would necessarily use for design, so it's not that accurate. It's not a high fidelity model, but it gives you a good sense of where to focus on and where the problems might be. So from here, as I said, this was all flood-related work, and we started working in Southeast Texas, and I did flood work there. And then obviously that's not the only issue that is going on. So we started thinking about how do we bring in heat, how do we bring in air pollution and other things. And so what I'll focus on today is more the heat part, and this is a paper that Matt worked on, and Matt is here. And so what we started thinking about is, can we detect events, multi-hazard events, so events where you have a flood event and a heat event that are essentially happening within a window of time, like within 30 days from each other. And so where the experience of a community is compounded. So essentially you not only have the flood, but you actually have a heat wave or you have a heat event combined with a flood event. And we wanted to do this from data that are open source, data that are available from satellites. So in principle, you could do this analysis anywhere. You don't have to have fancy observations to do that. And so we started with precipitation. So essentially, we use this IMER GPM daily precipitation data set. We essentially thresholded for a certain precipitation depth. And then we connect the precipitation depth to the return period through the NOAA Atlas 14. So we only collect those events that are about 2 years of return period. And then we merged all these precipitation events that are essentially within 200 kilometers from each other and within 3 days from each other. And we did some analysis to establish these numbers. But that essentially gives you a combined precipitation event, which we use as a proxy for flood events. And what you see here in the image is essentially that precipitation field, how the observations then are counted, and then you get these boundaries of this event as a clustered event that happened. We do the same thing with heat. And so the main limitation of the current the approaches that exist in the literature for doing heat is the fact that normally so you can use daily temperature precipitation like AIRS and MODIS, but then often the analysis is done on the 95th percentile for the minimum and the maximum. So essentially, you go and extract the days where the minimum and the maximum are above threshold. However, that doesn't account for the fact that in certain places, and Texas is definitely one of them, you may be below the 95th percentile and still be really hot, right? Because we spend summers of 40 degrees. So certain type of work, and especially road work or things like that, when you are at 30 degrees Celsius, that's really very much damaging from a health perspective. And so what we do is to combine the estimate of the heat wave as normally done, so with the 3 consecutive days where the max and the minimum temperature are above threshold, but also then combine this wet bulb globe temperature, and essentially is an estimation that account more for meteorological variables. We do that from satellite observations, though, so it's more like an estimate. But by using air temperature and relative humidity, we can identify those days where maybe this minimum and maximum were not above threshold, but still the temperature was above 30 degrees in terms of feeling, accounting for humidity. And then we identify these events, and then we aggregate these heat events with the same criteria as for precipitation, so within 200 kilometers and within 3 days from each other. And so you see here some examples of the largest that we saw in the record. So that's like the yellow is heat wave, the brown is more heat event, and then defined with the wet bulb, and the overlap hazard is the orange. So you can see that definitely Texas in particular, this is very relevant for Texas because we do get a lot of these combined events. And so then we can put these estimates together and calculate these multi-hazards events. So when essentially you have heat event and precipitation events happening essentially on top of each other or essentially within 30 days from each other. What you see on the left is what you would get, is the picture that you would get from the existing databases. So if you look at published databases, for example, for floods is the Dartmouth Flood Observatory, and you combine that with just the minimum and maximum temperature threshold, you get a picture on the left where the darker, but the more red is the color, the more you get to very extreme events. You can see there's a large part of Texas that in principle does not experience anything. But the reality is that when you look at the picture on the right, which is the method that we have developed, there's a lot more of these events. And in fact, what we found is that through the approach that we developed, we actually have a 5-fold increase in the prediction of how many events actually we have experienced. So you can connect then these with equity. There's a lot there, but essentially what you're looking at are Lorentz curves, which you may have seen before. So in the Lorentz curves, what you're looking at is on the x-axis, the sum indicator, for example, of vulnerability or race or economic status and so forth. And then what you're looking at is if your data plot on the diagonal that you see, it would mean that one of the two diagonals, right now, it doesn't matter. If you're on the diagonal, it means that each quarter of the population experiences the same, carries the same weight. So essentially, there's an equal distribution of how that hazard is impacting communities. When you see the curve, either the red or the gray, either one, and I'll explain you what they are, they see that they are well below the diagonal, they're below the diagonal. That essentially means that you have the most vulnerable part of the community that usually experiences or carries a lot more of the burden than the least vulnerable community. The comparison between the red and the gray is simply between the red is the method that we developed, the gray is what you get from the published databases. The important point here is that regardless of the method, what you actually get is that the most vulnerable communities are carrying the largest weight in terms of impact of these events. And one limitation, of course, of this approach, again, this is done from satellite data. So this is on a county level. And of course, when you talk about inequities, you actually want to zoom in more at the household. So there are some limitations, of course, to the resolution that you can reach with a method like this. The advantage is that you can do it from satellite, and that allows you to potentially do it in many other countries and not only necessarily in the States or in Texas. Okay. So what opportunities exist here? Again, this is just my thing. I'll give you some ideas as to where I think we connect. So first of all, I will point to this Belmont Forum as for an international consortium. Actually, the call this year is on resilience. And we are submitting one. Actually, Karen and George from here, from Eawag, are part of this effort that I'm leading. And there's other partners and countries, Cote d'Ivoire, Japan, Kenya, South Africa, and of course us in Switzerland. And the focus of these right now, the stage is pre-proposal, is on compound hazards and health implications. So the lead from Japan and the lead from South Africa are both environmental epidemiologists. And so what we're thinking about in this proposal is what are the health impact, physical and mental, of this compound hazards event. So this is already something that we're doing together in terms of me and Eawag, but there's other possibilities. So I'm just going to list other things that we are working on. So some of my group members work on improving hydrological predictions. That particularly is done right now in the context of the National Water Model, which is a US continental scale model for hydrological predictions, for stream flow prediction. We're analyzing precipitation patterns. This is also done in Texas in terms of clustering and how clustering may impact the flooding that we see on the ground. And then, of course, this call, we're submitting now a registration. And then if we get invited, the full proposal will be in February. So that would be super exciting. It's honestly very little money for what needs to be done. Everybody is absolutely underfunded, but it does provide an opportunity to create an international consortium and create relationships with other countries and other communities. All right, so switch to SWOT. Okay, so I talked about compound hazards. Now I'm gonna take you a little bit more on the graph and the network. And particularly what I'm gonna be focusing on is nutrient partitioning on graphs. So I would say that in general, this is more my sciencey side of the program. I like to think a lot about particles and particle transport on rivers. These are distributory networks, so these are coastal systems. The maps that you see were developed with a model that we developed. It's called Dorado, it's a Lagrangian transport model. So it's a model that routes particles, and those particles can have different buoyancy, which means you can be, depending on where you are on the water column. So if you're positively buoyant, you're traveling on the surface. For example, you could be seeds or pollen or things like that. The middle figure is for neutrally buoyant, so water, mud, nutrients, dissolved things in the water. And the picture on the right, negatively buoyant, are things that travel next to the ground, so for example, sand. These pictures specifically show nourishment, so the color indicates the fraction of the incoming particles that passes through that location. Okay, so essentially that tells you connectivity. Connectivity is a thing I'm fixated with. So I really like to think about rivers and think about how much stuff goes into the floodplain, because for deltas in particular, that's key to understand how these systems respond and are going to respond in the future. So in this context, the context for this in terms of project is SWOT. So SWOT, you may be familiar with it, is a NASA and CNES in other countries, but the main thing is the US and France. And it's the Surface Water and Ocean Topography mission. So this is a large SWOT altimeter. If you connected on Monday, there was a talk by Arnaud Cerbelot, who's on the science team as well, is a postdoc at JPL. Daniel here had invited him, so great talk, a little bit more on the details on what the mission is about. I'm going to tell you a little bit more about the science applications, but essentially this is an altimeter. So it gives you water surface elevation. Because of the way the orbit works, on average, depending on where you are in the world, but you have 2 sets of observations per month. The beautiful thing is that it's measuring things that we never measured before. So it was supposed to work for any river above 100 meters. I was at a science team meeting just last week. We're actually reaching less than 50 meter wide. So there's a lot of potential also for narrower rivers. And it's measuring lakes as well. So it's a very good measurement of water surface elevation and also water extent. That's super helpful because it's opening up a whole, I know Switzerland has great data, but when you think about global hydrology, that's not true. The beautiful thing is that this is an equalizer, there's data everywhere, and so you can really think about water balance and think about questions that we have not been able to address in hydrology. What we're doing within this and why this is not remote sensing in graphs. So what we're doing is global partitioning along river networks in deltas. So these are all deltas around the world, now all of them, but some of the deltas we're working on. There's a lot of work behind these networks themselves that we could talk about. So a lot of my research program also looks at that, extraction of water masks and extraction of channel networks. There's a lot of image processing, machine learning behind these things. As a convolutional neural network approach is fusing data from different sources. So there's a lot of cool stuff that we could talk about. But the point is that what we do with these systems is the following. So the idea of our project, when you're on the science team of SWOT, actually, you can do whatever you want. But there's actually also a funded project. And the funded project that I lead is on thinking about how fluxes of water, sediment, and nutrients are partitioned in deltas globally. So as you think about global extents, then usually numerical models are out of the picture, just because you need too much data and too many things to make them work right. The models that I was showing you earlier, the Louisiana case, I've worked on that for a long time. We have beautiful data from the field, from satellite, from the ground, anywhere. It takes a while to get a good model to run. And so we wanted to use the network structure. So we said, what if I partition fluxes based on the structure of the network? And so for discharge, for example, we already published that work. You can partition it based on the channel width, and that's actually pretty good. Essentially, 70% goes here, 30% goes here, based on the ratio of the width. But what we started thinking about is what can we do in terms of nutrients and in terms of sediment, and the part that I will show today is more about the nutrient side. I would also say that these systems move a lot. So those networks are networks that are being used when you have the SWOT data. SWOT needs a center line on the ground to actually translate the data that the satellite is taking to an actual location on the ground. So if you want to know if your river of choice or lake of choice is within that, for the rivers, you go on the SWORD dataset, and the SWORD dataset is the river discharge for SWOT. So it's a collection of center lines where you're guaranteed the SWOT data will be provided. And so we're essentially substituting these networks that I showed over, going the wrong way. This really went the wrong way. So I'm substituting those networks that I showed earlier. And because the networks in deltas are very hard to extract well, and so we're trying to get better data there. But the other thing I was going to say is that these systems change a lot. This is the Ganges and the Brahmaputra confluence. And what you're seeing is over the Landsat record, an analysis that we did of where water was appearing and when water was disappearing. So everything that you see red is water that became land, and everything that you see blue is land that became water. So there's a lot of dynamics. And so we're also thinking about ways to extract this through time. And so this project is also about hotspots and where things are changing and when they're changing the most in terms of hot moments. But let's get to nutrients. So this is the model that I was showing earlier. So we have numerical models for Louisiana that work really well. And so we're trying to use these models to see if we can then translate into a graph-based approach and then scale up the graph-based approach to global systems. Okay. Now, the main thing that you see here in these, so these are particles that are moving around. It's pretty fun to watch this type of model. So usually people get pretty mesmerized. I do too. But the thing is, the main thing that you will notice is that a lot of the particles go in between, right, the channels. So if you don't work on deltas, one thing you need to take from this talk is that deltas are very leaky. So networks lose a lot of stuff into the wetlands. In fact, in a system like the one on the left, 50% of the flows goes into the wetlands and then gets to the bank, to the bay from the wetlands. So the graph-based approach that I'm talking about will need to be corrected for this approach, for this process, because if you just work with center lines, you're essentially assuming that the mass remains conserved along the center line, but that's actually not true. So we'll get to that. So what we're doing then is to take these flow paths, so possible, this is still using a lot of the model results, so we haven't done this fully on the network only yet. But you can take all these flow paths, and these are all possible ways in which particles travel from the upstream location all the way to the bay. And this is work, by the way, that Ellie is doing. This is one of the chapters of her dissertation, and she's also here. And so what we do then is to say, okay, so how do we do nutrients? And nutrients, they go with the water, but then can we make an estimate of potential denitrification in these systems? Deltas are considered the last filter, essentially, before the oceans. But a question that we have is a lot of, in Louisiana, for example, a lot of the nutrients come in with the snow melt, so they'll come in the spring. The spring is also the time when the vegetation in the delta is very low. So there's a lot of connectivity, there's a lot of water, but that water moves really fast. So there's a lot of nutrients, but those nutrients are also traveling through the system really quickly and getting out. Versus there's a scenario in the fall in which vegetation grows, and vegetation acts as a sort of barrier between the channel and the wetland. And so there's less connectivity, and there's less nutrients, but when those nutrients make it to the wetland, they spend a lot more time there because the flows are really slow. And so the question that we had is that which of these scenarios is the most efficient in terms of potential for denitrification? So do I get more if I throw a bunch of stuff that moves really quickly through the system, or if I get a few, but then really make it to the wetlands, how long do they stay there? So residence time is a big thing here. It's actually exposure time. So what we do in terms of denitrification, this is very simple. So it's a sort of a stream spiral in theory. What we do is that we follow the particles in every step they take, and then we essentially apply a decay coefficient, a first order decay coefficient. And what we do is that depending on whether or not that is in the channel or is in the wetland, that coefficient will change. And so essentially what you see in the last equation is the case in which if the particle steps from the channel to the vegetated area, then we account for that as an average to think about how much mass am I going to have at the next step. And this way we essentially calculate how much nutrients I have in the water at the beginning, and then I can follow all these particles and get a sense of how much potential denitrification I have in this system. And so the maps that you see on the bottom, the left side and the right side is this fall and spring. The scale is the same, so you can see they have much larger potential for denitrification in the fall. So I have a lot more because residence times are much longer. Particles really do spend a lot of time in the wetlands, and that's potentially a good condition for denitrification to take on. Now, what we're doing now is the following. If I can take this same equation essentially and apply it on the graph. The problem with the graph is that it doesn't see any of these wetlands, right? So if I just have the network structure, I don't know how much water and how many nutrients are getting into the wetlands. So I cannot account for the leak. And that's where SWOT comes into the picture. So what SWOT sees is data like this. This is what is called a pixel cloud, is one of the products from SWOT. And essentially, this is classified. So it's classified based on whether that's water, whether that's land, whether that's other things. You can see them all listed here. Now, the deltas are very interesting because in principle, everything is water. But SWOT, in order for the signal to be nice and clear, really likes open water and really likes some roughness on the surface. So if the water is stagnant and still, it will be detected as what is called dark water. So the interesting thing here is that you see the map on the left is the spring condition, and the map on the right is the fall conditions. Between the two, vegetation blows up. So there's a lot of vegetation that actually is present in September that wasn't present in March. And so you can see this if you focus on any of the islands in between the channels, you will see they're very yellow in the spring because the flows are really going through. There's a lot of hydrological connectivity between the channels and the wetlands. When you get to the fall, though, there's a lot of this dark water. And the dark water is because there is vegetation. There's much less connectivity with the channel, with the island. And so we're devising way, this is a difference map between the two. And so we're essentially trying to think about ways in which we can estimate how much leakage I have into the wetland based on season from the signal of SWOT. And if we can do that, even if it's a simple thing like a percentage, then I have the potential to say globally how much water actually goes into wetlands and how many nutrients potentially go into wetlands, and then make an estimate of what areas would be most prone to denitrification. So of course, this is ongoing work, but we do see a lot of potential for SWOT to provide that information and modify this graph-based approach to be a little bit more physical. So what opportunities do I see here? There's a lot of stuff that we're doing in this area that I'm just going to mention. So of course, this is not only happening in deltas, but I do this work in rivers as well. So I do think a lot about river floodplain connectivity. I do work on migration rates. So we have ways to estimate based on particle image velocimetry, actually how much rivers move over time. And actually, we just submitted an SNSF proposal with a colleague in Israel in thinking about migration rates between rivers and coastal systems. We do a lot of work with the extraction of the water signal in itself, water masks, networks, sediment connectivity, nutrients, and so forth. One thing that I will mention, I was actually talking to CM this morning about causal inference. This is the graph that you see below here. One other thing in which I like to think about connectivity is process connectivity, so connectivity among variables and couplings among variables. So where the network nodes are the variables and when the links are the couplings between the variables. And so this is actually a study that we did in the same Louisiana Delta that you saw earlier. This is a transect of an island. Essentially, you're going from the channel to the island interior in the middle. And what you're seeing here is detected with information theory. This is actually a winter picture, and then we have done it also for the fall. You see all these arrows here. Essentially, the study shows that when I look at the water dynamics within the island and the sediment dynamics and the nutrient dynamics, they respond. They're very much in synergy with what's happening with the channel. So during the winter, because there's no vegetation, the dynamics within the wetlands are very much in synchrony with what's happening in the channel. I didn't put the other figure because there was no space, but when you do this same analysis in the fall, all the arrows that connect with the channels are not existent. And so you're really able to capture the switch between something that is controlled by the hydrology of the channels to something that is actually internally dominated. So when we look at turbidity, for example, it's actually resuspended locally and is not dependent on the channels themselves. So I think this is a lot of potential. I've been thinking about these tools for the Val Lab, that we have an experimental site at Hungerberg. What I can think about is hydrological data, but I also think this is very cool because I also like this as a way to improve models. So something I really like to do is to do this type of process networks for a field case and for a model, and to see what the model captures in terms of links. And when the links are missing, that tells you that your model is not good enough. So I like to think about that a lot. Okay. take a mental break for 30 seconds while I drink. So, last part that I wanted to show you is on humans. So I've been thinking about human dynamics a lot, because when I do landscape evolution modeling, and I think about rivers and delta evolution, humans are a major agent, and humans are nowhere in our numerical models. We're just no way to do it. We know how to model them. We don't have geomorphic laws for the action of humans on landscapes. When you think about how deltas evolve or rivers evolve, there's a lot of natural components, there's a lot of environmental forcing, but there's also human decisions. So for example, you may decide to build levees, you may decide to build river diversions, you may decide to build sediment diversions, right, or more water-based diversions. And these influence then the populations that are living there, so human decisions bring certain interventions, but also those interventions and feedback into the decisions. And so none of these is anywhere. So whenever we model landscapes, we model as natural landscapes. We have forcings, yes, we can maybe account for climate change, but you don't account for human decisions. And so the contest for this idea right now, I had a project that was just funded right before I left from the National Science Foundation in the US. And this is in the context of Louisiana. Louisiana is a place where there has been a lot of restoration. Some of that now is not really moving forward. But it's a place where this question really came very strongly, because as you decide, so river diversions essentially mean that when you have a river that has levees, you're essentially breaking that connectivity that I like to study so much. It's disconnected. That disconnection creates a lot of problems. So, the restoration of Louisiana really got a push after Katrina. When Katrina happened, the land was very depleted, and a lot of that is due to the construction of the levees, because there's no sedimentation on the floodplains, and so essentially land has been lost. Restoration, however, is a difficult thing, because when you start building diversions, for example, you're flushing a lot of fresh water down, and you're gonna go and change the pH of that water, and then fisheries, oysters, and things like that. There's a lot of interest that come into that picture. So the project that we have, which is led by Andrew at A&M, and I have a postdoc research associate now that will be hired at UT. The contest is understanding cascading feedbacks between human decisions making through different modeling approaches. So essentially, there is Moira Northeastern does a lot of co-design, co-engagement with communities, and so she has a model that we're now modifying to account for land growth that will be used with stakeholders to communicate how decisions impact the evolution of the delta. Andrew is focusing on agent-based modeling, and what we are doing in my group, and that's again work that Matt has been thinking about, is to do dynamical system modeling. And that's the thing that I will discuss today. So dynamical systems, so this is very much belongs to the kind of realm of social hydrology. And there were these very nice models that came out, particularly kind of a decade ago, and this is work predominantly led by Giuliano Di Baldassare and colleagues. But in thinking about how, to build a dynamical system model that really accounts for the co-evolution of the human and the water system, this model, you can see all the feedbacks here, plus and minuses, so how things affect each other. In particular, it was in the context of levee construction and led to the so-called levee effect, which essentially means that when you have your community that lives on a floodplain, you build a levee essentially to protect yourself. That brings you to live even closer to the river that has problems when there's floods because you're more impacted. But also you can't move too much away from the river because then you lose economic benefits. So it's kind of like an analysis, a very simple set of equations, but it allows you to understand, okay, what happens if people live closer to the river, build a levee, and what do they do? So essentially what we decided to do is to modify this model to account for what is defined as adaptive capacity. And essentially you can think about adaptive capacity as the capability of an individual or a community essentially to cope with changes, to adapt, to change quickly so that they can respond to hazard or things that are impacting them. And so most of the equations in the model, I will show them to you in a second, remain the same. So essentially the equations for the hydrology, the equations for the decision that the technology is whether you build a levee or not. There's a memory component. As people, when the flood first happens, your memory is really, really high, and then the memory decays over time, so you forget about the flood, so you move closer to the river. So there's a lot of these things. And then we added the adaptive capacity component to account for communities that have different vulnerabilities. So essentially, instead of working with one city only, working with two communities that may have different initial conditions, essentially in their capability of responding to hazards. And so these are the equations of the original model. I won't spend too much time on it, but essentially dynamical systems, you solve them. The beautiful thing is that you get the combined behavior of the system, and it's not something that you use for prediction. It's more a model that you use for hypothesis testing or even hypothesis generation. And so this is a typical result that a model like this will give you. So you have, stochastically generated water levels. So you can stimulate, the system with floods, and you can control, you have a distribution for these floods and inter-arrival time. And then you can see what happens when there's a flood. Then people build a levee, their memory spikes because there's a flood. And then, what happens to people and the demography, essentially also the economics, as you're more impacted, then that will decrease over time. So you can do then this to add this adaptive capacity component that essentially is a logistic growth equation, but then accounts for the fact that you lose the capacity of responding to hazards when you're impacted by one of them. And there's also an additional component, which is relief. So you can also get support. For example, the more affluent community may give you some support to respond to hazards, and then increases your adaptive capacity. And so you can get, an analysis like this. And essentially what we did was what Matt did was to then look at the median response in the United States. So essentially getting, information from census and GDP, you can get a sense of, again, this is the Lorenz curve that you saw earlier. So we can get a sense of how the median population in the US would respond to hazards and what happens when you have a more vulnerable community or a more affluent community. And what you can see is how their adaptive capacity varies over time. And of course, it's decreasing. And if a community is more vulnerable, it starts from a lower point. So they're actually more at risk initially, and then they're more affected over time. The other way in which you can use this model is to compare different cities. So for example, Houston and Beaumont. Beaumont is just attached to Houston. It's very close to it, but it's much smaller. And so they have much less resources. So you can see how they would evolve over time as subject to floods. But the moment you account for the fact that Beaumont is much smaller, so you have much less population, so many less resources, you can see already that their adaptive capacity is much lower. So this essentially allows you to compare communities and cities that have different characteristics and kind of understand what type of interventions, what type of decisions you can take, and how that's affecting their capacity of responding to future events. They're simple models. They're hard to test because you can't really, validate them in any possible ways, but you can use data. Essentially, what we're trying to do is to use data and make comparisons with cities and cases that we know of. The opportunities that I see here are the following. So first of all, we do have a tool, for example, for social vulnerability is one of the things that we use. Matt had developed that, the SV Insight. We have done a lot of this work also for understanding impact of floods on communities in terms of transportation and mobility and access to services. One way in which we're using the dynamical system model now is in a case of upstream to downstream communities. That's something that, at least with the stakeholders that I work with, comes out a lot. How a levee construction in the upstream community impacts then what's happening downstream and what type of flooding they see. That can be done with a model like this. And the other big thing is that we're integrating geomorphology in this model. So there's no social hydrology model right now that accounts for land growth. This is a model that we have developed in my group for land evolution. So this happens over centuries, over hundreds of years for sure. And then we're integrating a model like this to see how levees then impact land growth or land loss, and integrating essentially the geomorphology component into the social hydrology model. Okay, so this is kind of like a quick summary. It's hard to do conclusions with a talk that essentially talks about very different projects, but what I showed is in the context of multi-hazards, there's ways to detect these multi-hazards. So I like to think about floods and heat and other things that are happening simultaneously. So we're using satellite data to do that and understand how that impacts people. And what we see is that, of course, the vulnerable communities are the ones that carry the most weight. For graphs, this is in the context of SWOT and other work, but we have ways to partition fluxes along networks, and we're estimating connectivity from SWOT. I think we haven't finished that work, but I think there's a lot of potential. And then in terms of models, we do a lot of sophisticated models, but also these dynamical system models. I think they're nice to start thinking about how to add humans into hydrologic and geomorphic systems. And I will stop there. So any questions on this, but also on other things you have seen or general curiosity, I'll take anything. We have 10 minutes.
Paola. Thank you very much for this presentation. I really enjoyed it. I just was wondering about the Bangladesh and the rivers, you know, where they kind of converge. And all these kind of, you showed that there's water on the land and land on the water or something like that. Does it mean that there's a lot of erosion? Is it similar to erosion and deposition, or is this kind of an equivalent term?
Yeah, so if you're talking about the Ganges map that I was showing, yeah, so you can think about it that way. That's essentially a migration of the river. So where you saw the red is predominantly a channel that was there and has migrated where is blue. And so there's the way we do it over time is that it's not only small fluctuations, we actually track as to whether it's a behavior that is happening consistently, because otherwise you could have fluctuations for various things. But yeah, you can think about it that way. So it's not exactly a map of the geomorphology and what's happening, but it is close to that. And there's actually a colleague of mine, Cornell, Austin Chadwick, is used similar approach with PIV to really track the banks. So I think when you get erosion and aggradation, then it's nice to track not necessarily the center line and the water mask, but actually what the banks of the river are doing. So you can get to that. And I think, you know, in thinking about communities and in thinking about adaptation, information on migration rates is very much not accounted for. Right? It's not usually in risk frameworks, but it's super important for people to know, you know, where you're living with respect to what dynamics your river has over time.
So what does it mean, looking into the future, if there's maybe less water coming down the river, or the pattern is different over the year and we have sea level rise?
Yeah.
Can you kind of use this approach for these kind of questions?
Yeah, I mean, I think, you know, in what we're doing and what these tools give you is you can track over time which areas of the river network are more active, right? So you get a sort of glimpse at the hotspots. I don't know yet what those are. I can tell you that in the Ganges, for example, of course, the braid is very, very active, you know, this part of the system. When you have tides, usually the tidal part is very stable, so you don't see many changes. The other interesting thing, I didn't get into it today, is that when you look at the area where those polders and those levees are constructed, because of the construction of the wall between the river and the floodplain, the sediment remains in the channel. And so those rivers, in some cases themselves, have become red because they're silting up. So you see a lot of those changes over time. So then you can ask the question, that combined with migration rates, then you can relate it to, you know, frequency of floods, and you can relate it to kind of the studies that I showed at the beginning, thinking about with climate change, what are we going to see in terms of frequency, and you can make some inference as to what migration rates or what behaviors you're going to see in the geomorphology in the future. One thing that, you know, one of the biggest unknown, I would say right now, you know, for us, there were modelers, you know, when you model a river system, usually you have bathymetry that is a mosaic of bathymetry collected at different times, and then the flood happens, and normally you don't account for that change over time. So I think a big unknown and a thing that would be good to resolve now, I think we made a lot of progress from climate to hydrological predictions, but how that hydrology and those changes in the hydraulic and hydraulics in the river impact the geomorphology, that's a big unknown right now, but that has huge implications for people. So yeah, I think with these tools, you can get a sense of where things are changing the most, and then probably those are things that locations I would monitor more carefully, or where I would, you know, do some good analysis of where communities are actually located.
Thank you very much, Paola, for this wonderful overview. I'm intrigued by this coupling between what the river does and what people do, the third part. And so the first question is it true that you understand one side of this relationship probably much better than the other? So that it's easier to understand what technical infrastructure built by humans does to the water. And is it true that it's much harder to understand what events, floods, and so on do to human behavior? And so my question is, how do you go about this, and how do you parameterize this part of it?
Yeah, no, it's an interesting question. I don't know how to answer it. I think in the context of the current model, I'll answer first in the current model, but I think the answer can actually be much wider than that. in the current model, you essentially parameterize how the hydrology is affecting people specifically through a water level, right? So you essentially control that. Is that the only way? No. With the geomorphology, I think what we can get at is the additional component of if I build a levee, then I also create land loss, and that is a bigger impact. And then if I put sea level rise, then it's additional impact, and we're building we're building those components. There's some limitations as to what you can do with a dynamical system, of course, but I do think it allows you to understand, well, it kind of gets you a sense of where to look and what are the couplings that, are most interesting. I don't know if it is true in general, like regardless of the model. I don't know if I would lean one way or the other one. Like I'm not convinced that we know all the ways in which our interventions are affecting the natural system, because it's a big temporal aspect of it that is often hard to grasp. And I think, coming from an engineering background, knowing that, we always thought about structures and life of structures for 50 years, the truth is that then we've seen how all the structures beyond the 50 years have really had bigger impacts on ecosystems, on fish communities and things like that. And I think a lot of those feedbacks are not something that we are measured, and we're starting to see a lot of the impacts, because a lot of this development really blew up in the mid-1900s, so we're starting to have data to detect that. But I think the spatial temporal scale, it's a super interesting aspect as to what you see immediately. Then that impacts the human decisions, because I feel like, if you are taking a governance-like decision on how to protect the community, the levy is going to be a very popular decision because people are going to feel safe. With restoration interventions, sometimes you get 40 years to get something going. Who's going to wait for that? And then in the meantime, you have all these other things that you change the system regardless, right? You change the system when you put the dam, you change the system when you remove the dam. Nothing is free. So I think it's a complex question. You don't solve it with a dynamical system model, but I think at least is a beginning of thinking about human decisions in geomorphic models.